Assalamu alaikum guys, I hope you're doing well. So today we are talking about a very important topic about cloud security checklist, but mostly focus on from coding perspective. So the topic is code to cloud security checklist, which involves various phases like secure code training, scanning the API and its documentation, automatic threat modeling. So what is code to cloud? So code to cloud is a framework that centers around requirements for cloud native application development and builds application security into every steps of software development lifecycle, from the first line of code to deployment and runtime in the cloud. So what does this mean for the team who are involved in this? So in a code to cloud AppSec program, developers and the AppSec managers must be aligned, since they must work together to identify and remediate vulnerabilities found at in every stage of development. So in theory, this close alignment, visibility into the software development lifecycle, and ability to remediate vulnerabilities before deployment can help enterprises protect their business critical applications. However, this approach has its unique challenges. So these are the statistics from various sources like IBM. So 45% of data breaches happen in the cloud. 73% of business have cloud-based application, and 76 of organizations say that the number of point tools they use cause blind spot. So how did this evolution happen of cloud native application and impact and significance? So cloud native application have changed the way software is designed, deployed, and managed. These applications differ significantly from traditional monolithic architecture in several ways. So the first one is the microservices. So microservices based architecture, also known as composable application, make it easier to scale application across cloud environment. Organization can deploy and scale individual component of application as needed rather than the entire application. In addition, a microservice based architecture allows for multiple development teams to develop and release different part of application in parallel. The second is the application programming interfaces, or APIs. So micro-based architecture have driven an increase in the use of APIs. APIs are used to communicate and improve interoperability between the microservices and third parties. They also enable multiple development teams to work on different components of application, knowing how these microservices will communicate with each other once deployed. Then next is the containers. So the need to rapidly scale application across multiple cloud environment requires increased standardization in how applications are packaged. Container platforms like Docker provide an abstraction layer that enables developer to focus on the code specific to their application. Container packages an application and all its dependency in a way that it can be consistently deployed across multiple environments, including different cloud providers. Number 4 is the infrastructure as code. Deploying an application can require configuring many different infrastructure components, with the cloud enabling applications to be rapidly scaled up and scaled down. These configuration tasks are potentially performed on a repeatable basis. So IAC, or infrastructure as a code, automates infrastructure deployment using code, enhancing consistency and reducing manual errors. For example, AWS Cloud Formation enables defining and provisioning AWS infrastructure in a reproducible and efficient manner. And number 5 is the DevOps. Cloud native application development has driven adoption of DevOps methodologies, with hundreds and thousands of microservices being developed in parallel. Organizations need to operationalize how applications are developed, built, delivered, and deployed consistently at high scale and velocity. While DevOps mean much more than just require technical capabilities, it has driven increased automation of different development steps and tasks across the SDLC. So 83% of the organization have more than 50 of their apps deployed in the cloud. So what are the challenges with regards to securing cloud native applications? So the impact of the cloud native application can be immediate, facilitating speedier innovation cycles, deployment, and communication between development and AppSec team. However, the transition to cloud application have some challenges. The microservice challenge. So the agile development model enabled by the microservices can challenge AppSec team. A single application can now be comprised of dozens or even hundreds of microservices, each an independent software project worked on by different developers on a different release schedule, and that must be independently scanned for vulnerabilities. The second is the challenges is from the proliferation of APIs. So the proliferation of APIs have created new security challenges, including data exposures caused by shadow and zombie APIs. Shadow APIs are undocumented and unknown to security team, while zombie APIs are abandoned while remaining in production, both pose security and compliance risk. Next is the attack surface expansion. Containerized environment can expand the attack surface and require individual component production and micro-segment, particularly in Kubernetes control panel. The short-lived nature of containers makes it difficult to investigate security issue, and their reliance upon the open source component increases security risk due to the vulnerabilities that are potentially exploitable by the attackers. And next we have the IAC risk. So infrastructure as a code templates allow for potential misconfiguration, which can result in exposed sensitive data or compromised access control. Storing IAC template in insecure repository repositories may invite malicious manipulation, resulting in security breaches. Additionally, challenges like configuration drift, unintended changes in template over time, and ghost resources, untagged asset with potential cost and maintenance can result in even more security implications if not monitored and addressed. So that comes the need for secure cloud native application lifecycle. So securing cloud-native application presents a unique set of challenges. As the pace for development continues to increase, it is becoming harder for AppSec team to keep up with development. AppSec team often find themselves with multiple security tools to use at different stages of the SDLC. This introduces another layer of complexity since these tools all must be managed separately and many don't integrate with each other. Without that unified view and overwhelmed by the number of potential vulnerabilities, AppSec managers often try to slow down the development process to remediate issues or choose to release applications with known vulnerabilities. One of the most impactful ways organizations build trust between the AppSec and development teams while also managing tool sprawl is consolidating their tools into a unified platform. For example, like the checkmarks one, having teams work with unified platforms not only gives them visibility into the entire SDLC, but it can also help team become more efficient with vulnerability identification, their prioritization, and remediation. When enterprises invest in building trust across their team, they often can develop a more secure, effective SDLC that align with dynamic nature of cloud native application. According to Checkmarx 2024, 90% of the organization have deployed known vulnerable code in production to meet business or features deadline. And also 78% of organizations have at least one breach in the last year as a result of vulnerable application they developed. So let's talk about the application security in the cloud native application lifecycle. So AppSec teams have known for years that different vulnerabilities can be introduced or become apparent at different stages of SDLC, such as with SST, DST. More recently, application security has embraced a SIFT everywhere approach to securing application development. When thinking about a code to cloud AppSec strategy, it's important to fully understand the complexity of SDLC. Securing application effectively requires a holistic AppSec strategy that focuses on building security from the first line of code through deployment and runtime in the cloud. So organizations find vulnerabilities at every stages in the software development lifecycle. So you have the first stage as the design, code, check-in, build, test, display, go live, and the feedback. And so as per the survey, it is estimated that 37% of vulnerabilities are found in the design phase, then 40% during the coding phase, 32% during the check-in phase, 31% during the build phase, 29% during the test phase, and 20% during the display phase. And still there are remaining 12% during the go live production phase. So let's talk about the design phase. A code to cloud approach to application security starts with proper designing. The design phase enables multiple development teams to work on all different microservices in parallel by defining how the components, subcomponents, and architectural elements come together from security perspective. API security. So the proper API design allows developers to scan documentation files to identify potential security risk and misconfiguration that will appear once in production before writing a single line of code. Documentation can be shared with security team to apply the proper runtime security control when the application is live in production environment. Maintaining and updating API documentation as code changes over time can help identify inadvertent introduction of security risk into the environment. Threat modeling. So threat modeling can provide security recommendation and requirement upfront where they can easily be integrated into the coding phase. In addition, using threat modeling can enable AppSec and development team to reach agreement on how application will be built, including when and where security controls are applied. The coding phase. So once application is designed, developers then translate the blueprint into functional reality by creating the code base through a combination of source code that they write supplemented with open source and third-party software components. We can have secure code training. Most developers have not been sufficiently trained on application security risk or implementing security coding techniques to mitigate risks like injection attack, buffer overflow, and other common vulnerabilities. Improving developer security skills can not only benefit developers but also reduce the number of vulnerabilities that make their way into code. Having a static application security testing. So scanning source code for vulnerabilities is the foundation for any AppSec program. However, many SAST solutions require finding the most true positive with the least number of false positives. When applying a SAST solution, organization must consider requirement of each application. Business critical application can benefit from tuning to identify maximum risk. However, the need to cover every application requires low false positive out of the box for less critical application, even at the expense of lower true positives. API security for cloud native application. Understanding the risk often requires seeing vulnerabilities through the API lens. Displaying detected vulnerabilities for API allow AppSec and development team to prioritize risk by API. Discovering the API while scanning code can be much more effective at inventorying all the APIs in an application. The global API inventory can then be compared with the API documentation to identify shadow and zombie API that were previously missed and are likely not protected in the production environment. Next is the secrets detection. In modern development teams, developers within and across different teams must collaborate when developing applications. It involves sharing of secrets, which can include password, APIs, keys, cryptographic keys, and other confidential data that developers need to collaborate, but should not be exposed to unauthorized users. Supply chain security should start in coding phase by identifying secrets shared in collaboration tools and preventing accidental leakage. Next is the building phase. So the build phase is where the applications start to take shape, secure code is compiled, and executable files and create a foundation for application. Developers often build tools and systems to automate this process to ensure consistency and generation of deployment artifacts in the larger stages of deployment. There are something called software composition analysis. Compiling code and building the application start to pull in open source libraries and other dependencies. Securing these third-party components and mitigating several vulnerabilities is essential for robust application security. An SCA solution will identify vulnerabilities in open source libraries, present abstract teams and developers with remediation options. Malicious packages protection. So open source security has evolved beyond just identifying vulnerabilities inadvertently introduced to an open source projects. New threats include malicious code intentionally contributed by attackers to be exploited. Once the application is built, modern open source security now identify malicious code to guard against potential threats. Software bill of materials. So upon disclosures of a new zero-day vulnerabilities, organization need to quickly identify if any application in the environment includes vulnerable versions. This is complicated by the cloud-native application architectures, simply by the increase in number of different application components that must be validated. Having the SBOMs for every software project along with proper SBOM storage and operational processes can greatly simplify response. This is where the application is deployed into the production environment. Next, we have the testing phase. Here, we test the functionality, performance, and security of the application. Developers utilize various methodologies such as the unit testing, integration testing, system testing, and penetration testing to identify and fix any issues. This is another place where automated tools help, since they can help ensure comprehensive test coverage and expedite feedback to the development team. The dynamic application testing of the compiled code is crucial to pinpoint vulnerabilities, weaknesses in application logic, and code base. Neglecting dynamic testing could expose the application to attacks that are only apparent once compiled. Having a penetration testing, whether using DST or the tools, will help uncover vulnerabilities and weaknesses in the application, such as vulnerable third-party components and data leakage and session management issues. Being aware of this issue at this stage will allow proactive remediation before deployment. 100% success rate detecting and confirming vulnerabilities and tested. All right, let's move to our deployment phase. So with cloud native application, this stage involves configuring servers, setting up databases, deploying application components, CI/CD pipeline, having a container security. ISC security is very important in this phase. And then is the go live. So having cloud security, posture management, web application and API protections, container security. These are all essential for having the application security integrated into the development environment.